From Team Germany, and today I will record problem number 3, Siren. The problem description reads as follows. If you direct an airflow onto a rotating disc with holes, a sound may be heard. Explain this phenomenon and investigate how the sound characteristics depend on relevant parameters. Let's first examine what a sound actually is. A sound is an oscillation of pressures or a particle displacement propagated in an elastic or viscous medium. This oscillation could, for example, look something like this. You can see that the denser regions in air correspond with the maximum of the sine wave. The frequency of the oscillation thus determines the pitch, and the density, the loudness of the tone that is perceived. We'll investigate the parameter of pitch in the first part of my theory. However, sounds that we frequently hear are not perfectly sine waves anymore. The amplitude profile over time could look, for example, something like this, which is a 440 Hz tone played on a piano. One may notice that this sound is in fact still periodic, but just not purely sinusoidal anymore. In fact, sounds like these are made up of a sequence of harmonics whose frequencies are integer multiples of the fundamental frequency. Fortunately, sounds like these can be expressed as an infinite sum of sines and can thus be investigated through a fast Fourier transformation. The FFT then shows us the intensity of each harmonic, and the intensity of each mode in this case is measured relatively to the intensity of the fundamental frequency. The resulting profile could, for example, look something like this, and is commonly referred to as the timbre of a tone. We can see that the timbre of a 440 Hz tone played on a piano is quite different, for example, to a 440 Hz tone played on a violin, even though the fundamental frequency is, of course, the same. This also explains why the same note played on two different instruments sounds fundamentally different. We'll investigate this second characteristic of sound, the timbre or timbre, in the second part of my theory. Furthermore, it's very important to note that the error assessment in all of my measurements for the frequency was done by taking the full width of the half maximum, but this error was typically very small and even below 1 Hz. The tone of the Siren disc is perceived through the periodic change in pressure created through the periodically overlapping holes. When the air outlet and the hole overlap, air flows through the hole and a pocket of high pressure emerges behind the disc. When the air outlet and the hole do not overlap, however, there is no airflow through the hole and thus a low pressure behind the disc emerges. Due to this periodic change in pressure, a sound is heard, and I don't think you can actually hear this sound right now due to technical issues, but maybe you are. This is what it actually sounds like. Going on to my experimental assembly. My experimental assembly consisted of a metal frame where the Siren disc with one backplate on each side was held in place and thus stabilized axially. This disc was then rotated through a stepper motor, which was controlled via a microcontroller. The frequency was additionally measured independently with a laser and a photodetector, as you can see here, and the air outlet was placed here. Was connected to a compressor. The 3 different air outlets I used all had very small radius compared to the length of the pipe to ensure laminar airflow inside of the pipe. Behind the disc, I placed a directional probe microphone to measure the sound, and between the air outlet pipe and the holes of the compressor, I installed a T-fitting to connect the pressure sensor to ensure the reproducibility of each measurement. The data from the microphone, the pressure sensor, and the photodetector were then saved onto 2 oscilloscopes. Each measurement was 2 seconds in length with a sample rate of 2 microseconds, resulting in 1 million data points per measurement. The microphone response curve of the probe microphone between 50 and 2000 Hz has a slight linear slope, as you can see in the beginning over here, but we'll take a closer look upon that later on. The raw experimental data saved on the oscilloscope often looked something like this when zoomed in. We can see that the pressure is quite constant over this period of time, and furthermore we can observe that the curve from the hole overlap actually, measured by the photodetector, corresponds very well with the resulting tone, which is displayed down here, which thus proves our previous assumption made in the basic explanation that the tone is created through the overlapping of the holes. The fundamental frequency of the tone should therefore result from the frequency of the disc multiplied by the number of holes. The number of holes thus determines the slope, and the resulting tone frequency as a function of the rotational disc frequency should look something like this for 25, 30, and 50 holes. and the experimental data does in fact prove this theory right. If we want to examine the timbre of a tone, however, we need a more sophisticated theoretical model. Mathematically, the overlap of two circles resembles a convolution of two functions. The resulting graph of the convolution, displayed down here, shows the amplitude over time and should approximate the amplitude function of the tone itself. A similar theory that utilizes the convolution of the Holtz to predict the timbre of a tone was first proposed in 1921 by Edward Arthur Milne through a numeric equation. What this theory does not consider, however, is the convolution of two different sized holes, which we can see looks quite different to the one of two equally sized holes, and it does not account for the velocity profile through the pipe. Because the velocity profile of a laminar flow through a pipe is approximately quadratic, the resulting convolution cannot simply be done with two holes. To account for that, I split the convoluting circles into a defined number of pixels and gave each pixel a numeric value adjusted to the quadratic velocity profile of Hagen-Poiseuille. I thus utilized a simulation to solve this convolution. The input parameters of my simulation thus were the radius of the hole, the radius of the outlet, the number of holes, and the parameter of scale, which basically means the number of pixels per millimeter. The simulation then counted the overlapping pixels and multiplied it by the numeric value, thus giving us the amplitude as a function of time. Before comparing the theoretical model to the experimental model, however, we need to take a closer look at how microphones actually work. The amplitude of the experimental data, in our case, is directly proportional to the amplitude in decibels. This means that the experimental amplitude is actually the logarithm of the measured pressure divided by nominal pressure and adjusted by a factor alpha that is frequency dependent. A factor alpha like this is used in almost all microphones and is actually to adjust the amplitude of the sound to the human ear. For our experiment theory comparison, this means that we also need to take the logarithm of our theoretical data divided by the nominal 1 and adjust it by the same frequency dependent factor alpha. Alpha can in this case simply be taken from the slope of the microphone response curve between our measurement range, which was 1.454 times 10 to the minus 3 decibels per heart. Analyzing the adjusted theoretical data, we can plot the intensity of each harmonic as a function of the changing parameter, in this case the hole radius. N in this case indicates the number of the mode, so this would be the fundamental frequency, first, second, and third mode. The dashed lines represent the experimental data, while the continuous line represents the theory. We can observe that the theory actually matches the experimental data quite well. On the left side, you can furthermore see the convolution when the hole radius is very small, and on the right side, you can see the convolution when the hole radius is very large. We can see that as the hole radius increases, the area under the graph increases as well, resulting in an increasing amplitude of the fundamental frequency as displayed here, which is because the intensity of the fundamental frequency is simply the integral of the convoluting function. Changing the varying parameter to the outlet radius, we get these graphs. In this case, it is important to mention that I adjusted the pressure to get the same absolute amplitude with every outlet. We can see that the absolute amplitude does not fit quite as well as for the hole radius, but the progression is still valid within a certain error margin. The deviation at the 2.5 millimeter outlet hole is quite large sometimes and can be explained as this outlet was in fact not circular but rectangular. So we conclude from that that the simulation would need to be adapted accordingly to accurately predict the outcomes of rectangular hole outlets. Moving on to the number of holes, we can see that aside from some measurement errors, the absolute amplitude, the theory does predict the progression of the experimental data again. The decrease in higher modes can be explained as the convolution with increasing hole number gets a less steeper slope, as can be seen here, with a very steep slope at a small number of holes per disc and a very less steep slope with a very large number of holes. And you can thus, these functions can thus better be approximated with less overtones as the slope is, as I said,
你建议
less
他
steep.
放一张全部可以底图，然后
Although
用
the
笔
progression
画，因为
profile
它
of the
从
theory
来没有
of
这
the
样，
three parameter
然后就可以
variations
看出
is
小
to
屁
fit the
因为它
experimental data
忽
in
略
most
到，
cases.
然后
We
用
can
笔写的
undoubtedly
时
see
候
some
看小屁
offsets
会
or
有有趣
deviations
现
in a
象。
couple of points. These deviations could be due to some inherent limits of the theory.
它
Considering
只
the airflow, I assumed that the flow through the pipe was laminar with a constant velocity during my measurements. Additionally, the theory neglected any turbulences that might occur around or behind the disk. Regarding the geometry, the theory assumes that the center point of hole and outlet are identical and neglects the distance between the outlet and the disk. Concerning technical assumptions, the disks were assumed to be axially stable and assumed to rotate at a constant frequency. And nonetheless, we proved that the simulation can predict the experimental outcomes in spite of these limits, especially through the progression of with a convolution at the basis of this theory, we can design a disk that should produce a tone that is very pure and with almost no harmonics, a sine disk. We can observe that this assumption is in fact valid. Aside from some minor overtones at 400 and 600 Hz, we can see that the tone is almost exclusively defined by the fundamental frequency at 200 Hz. And even has no other overtones above 600 Hz, over 5% of the fundamental frequency. In conclusion, we looked in the basic explanation, we first looked at what a sound actually is defined by, and found that the relevant parameters are pitch, loudness, and timbre. We additionally looked at the I'm sorry. 1 second.
对，然后他也没有讲他的 amplitude 是相对的还是觉得
Alright, here we go. We additionally looked at how a sound of a siren disk actually comes from. In the first part of my theory, we then investigated the pitch and the relationship between the frequency and the pitch. Then in the second part of my theory, we investigated the timbre of a tone through looking at the convolution of two functions. And using a simulation, we varied the parameters of hole size, outlet size, and hole number. And finally, we looked at the special case of a sine disk and found that disks such as that are able to produce a very pure tone. And then, thank you very much for your attention.
Wow.
Okay, thank you. Well done. We move straight on. We move straight on to the proponent, who's got 2 minutes for questions.
Okay, thank you. Thank you for the presentation. First, the question I would like to ask is: do you measure the width of the disk, which is which you can see as the disk, length of the hole? Measure
The length? Do you mean the? Yeah, but do you mean the distance between this center hole?
the thickness of the disk.
The thickness of the disk. I did not measure it, but it was quite small, probably under 2 millimeters.
Okay. So, do you think that when the air goes through a hole, it will provide the sound without rotation?
No. No, without the rotation. No, without the rotation, no sound will be seen.
Okay. So, did you place the microphone right in front of the holes or for distance?
I had a bit of distance. Maybe I can show later in the presentation. I think I included a picture in the appendix. But it was placed at a certain angle to not be in the not be in the airflow itself.
So, do you see any other peaks in your sound spectrum instead of the recording? I believe in page 28 you show some small peaks in your spectrum.
Yeah, of course, there's some deviations always. Those ones here above 50 Hz are typically from machines running. So this basically like motor sounds or something are almost exclusively in multiple integers of 50 Hz. So this is like 2%, 4%, it's under 5%.
So is there any limitation of maybe like the boundary conditions of your phenomenon? So the thing I'm going to consider whether air flow can go through at 2 holes at a time.
Well, yeah, but usually in all experiments, actually, my outlet was so small that no 2 holes could pass through at the same time. So this is not a case that I consider.
Okay, thank you. That is time. We need to move on to the preparation of the opponent. And you've got 5 minutes. Oh, sorry, I'm getting wrong. No, 5 minutes.
答案跟问题要答对，然后大家想想。有吗？好吗？
但是大概是用 omega 吗？还是用什么？
哪一个？
说 F 吗？就是它
那是 F 等于 F 乘以 N。
F 一定有转速这个变音啊。
他没有做转速这个变，哎，他有做。
那个 F 啊，
他是 F。
那盘子转速是 F omega 是没有啊，是盘子的频率。H 痛还是放着？叫你 H 痛还是放着？看我忘记原因在哪里。那也就是说 ，no expansion 的放着。那个角色，他只是他们少的东西。H 痛很重要吗？我把摇出题。不要了，不用了。分半，最后检查一下，检查好再涂上去。
See your sharing screen. Are you ready yet? Do you need more time?
Maybe I can start present now.
If you're ready to go, Danny, if you start the time for the presentation, so you have 4 minutes and then 10 minutes discussion. Good luck.
Okay. Hello everyone, I'm essentially from Taiwan, summarizing problem number 3, Siren. And we can first look at the problem statement. The problem statement asks us to analyzing the sound characteristic, which I think the reporter should mainly focus about the spectrum about the different experiments. But the reporter only shows the comparison between different harmonics, so I think showing the spectrum may help us to more understanding about the sound characteristic about the sound and about the source of the sound, the reporter mentioned about the simple harmonic and also analyzing some of the different cases instead of using the siren. And and for the quantitative explanation about the characteristic frequencies, which is a spectrum. That is a different area about higher pressure and lower pressure, which will discuss the compression with. And there is the fundamental in the sound that can mostly be heard by the human's eyes that will be related to the frequencies of the disc. And for I think the recorder have the well demonstration of the origin of the sound and also explain the physics behind the sound by using the fast forward transformation. That's the combination about some sinusoidal function. But I think the recorder has ignored the turbulence at the host. I think that is very important. But in this case, since by blowing the airflow without the rotation, it will still cut the sound such as blowing a whistle. And the recorder can element noise in the environment without any sound absorb box and also have the deviation over the frequency. And for the modeling, I think the recorder mentioned about the frequency proportional to the host frequencies and also intersection area have been considered in this theory. And the relative intensity may be affected by both this and also the area. And I think the recorder has completed the calculation of the fundamental frequencies and also the waveform about the sound. But and the amplitude differences inside the host are also being mentioned, but he didn't mention the boundary of the mode, such as the rotation without the rotating, or also that the air will go through in the two hosts at a time, and also the sound intensity related to the air flux, wind flux of the host. And for the characteristic, the frequency analysis, and using different radius of the host and number of the hosts as his experiment, and he also showed a very interesting cases, which is a sign-shaped disc. And for the frequency level proportional to the air penetrated, which will related to the number of hosts and also the angular velocity. I think the reporter has found a linear relationship between frequencies, but it has some of the large deviation that he expected, and also only consider the 3 harmonics. I believe there will be more, and also didn't explore about the unexpected peaks in some of the spectrum, and didn't find the limitation of the experiment, and also no mention about the H-tone, which is the sound that comes from the air goes through a host. And for the intensity analysis, the intensity may affect by the diameters of the host and also distance between the hosts. And I think he has well quantified the relative intensity in different harmonics, but I think showing the spectrum will make us more realizing how well the sound distribution into the different harmonics. And for the discussion point, first I would like to present how the relative intensity in the harmonics will show like, and also how did he verify his experiment by using different experiments, since the intensity may be the relative intensity, and how the high frequencies part acting light, which I think which is the most part about the air H-tone, which is the air sound comes from air goes through a disc. Is there any H-tone appears by the host, and how do we excite the air H-tone as a harmonic, and what's the limitation of the relationship?
Okay, thank you. That is the end of your time. If you want to move into discussion.
Please turn to page number 17. I believe that
I would need presenter rights for that, please. That would be great. One second, please. So is page 9 you said?
Yeah.
So this one here.
Yeah. Since you have placed your microphone in such a distance between the hosts, is that correct?
I can actually show you quite well. 1 second. So this was basically the placement of the microphone. So I didn't place it entirely into the airflow to reduce any noise that would just come from the flow itself. But I wanted to observe the tone, right? That's what's stated in the task. So I placed it at a certain angle and at a certain distance to, as I said, reduce any disturbances.
So, okay, I think that is quite well to reducing the sound comes from the airflow. But in my opinion, I think when you place the microphone for such a distance, the airflow. First I would like to talk about when the velocity of the airflow is not quite stable or fast enough that it will still cause some turbulence and it will go through about the side of the holes. So in my opinion, I think placing the microphone inside of the hole will be causing some of the sound being influenced, like the waveform it shows. We have shown some different waveform in the same periodic, so I think the sound may come from when the airflow goes through the single holes, it will still come. It will show some sound without the rotating. Such like
excuse me. Yeah, excuse me. So first of all, my velocity was quite constant over time. Actually, you can see that I measured the pressure over time. So velocity and pressure are, in this case, related to one another, and you can see that my pressure is, aside from some very small deviations, actually quite constant over time. And at the same time, the airflow was only allowed to go through one hole because I placed the air outlet actually under 1 millimeter in front of the disc. And there was, in this case, the hole and the outlet were approximately the same side. I think the holes were 0.5 millimeters broader than the radius of the outlet. So in this case, there's no reason to assume that the air would go through two holes at the same time. This is actually what my experimental data shows as well.
Yeah, so you didn't consider the limitations such as blowing the two holes at a time. So I can understand that your setup reducing such as deviations. But the thing that I want to ask is that the noise comes from the surrounding, and how do you reduce the noise?
Well,
you have any of your setups?
Well, I mean, I'm sorry, but this is probably noise lower than like 5% of the actual peaks. So you can see that the noise is really irrelevant actually to the problem itself. I mean, this is motor noise probably, because motor noise is usually about 50 hertz, but this is a very good experimental data actually. I mean, it's like, I mean, the peaks are like 20 to 30 times the size of the actual disturbances, which is basically as good as it gets.
Okay, sorry to interrupt you, but the reason I would like to discuss it, seems that in these cases we can see that when n equals to 3, which has a very small intensities, am I understanding correct?
Sorry, can you repeat please?
So the intensity will reduce while increasing the different harmonics. So when the harmonic is very small, the intensity of the harmonic is very small, the noise will interact the harmonics. So let's move on to the next structure, please. Please change to page 617.
To 17, sure.
Yeah. That you show the experiment about the frequencies. Yeah. So first, there is not such as an error bar that in your experiment. That is the first question. And for another question is there any deviation caused by the small intensity of the sound?
Well, first of all, you can see that error bars in this particular case wouldn't actually make lots of sense. I wrote down, I don't know if you can read the text. It says that the horizontal errors are below 0.05 hertz, which has been done. Well, the error assessment has been done with the full width of the half maximum. I explained that in the first section of my theory, and divided that by the number of holes. This was taken by the full width of the half maximum of the laser convolution, and then the vertical error bar is just of the half maximum.
You have quite match for the theory and the experiment. But the question I think is, since the sound will create different harmonics, I think that it will be creating different amounts of the harmonic in different spectrum, or like a different experiment.
Well, yeah, of course, but this is basically what I looked at in these graphs over here. I don't know if you. I mean, this is basically the spectrum of the sound. You can see that that n equals 0 basically is the fundamental frequency, and the intensity of each radii. Well, plotted on the x-axis, we plotted the different radii of the holes, and then the intensity of each harmonic. In this case, the fundamental, the first, second, and third harmonic. So this is basically the FFT spectrum, just plotted in a different way, so that the x-axis in this case is the parameter variation.
Yeah, I can understand your the thing that you're doing, but the reason is that the intensity in your spectrum is relative intensity, so that is you can't just compare it in different experiments at the same time. So the reason I'm curious
this is actually not true. I need to correct you on that. In this case here, this is absolute amplitude, corrected by the factor that I explained over here. In the case of my basic explanation, like in this graph over here, that was relative intensity, but that was just for the sake of explaining the actual phenomenon. So the absolute amplitude in this case wouldn't have been of any importance.
Yeah, please turn to page 25.
Yes, please.
So in my opinion, in these cases, you can see that when n equals to 0, the theory is much lower in your theoretical prediction, but when the n equals to 3, the theory is much higher in your theoretical prediction. In my opinion, I think it will cause by the H tone that will cause the small peaks that giving a deviation for the experiment. Is that correct?
Sorry, can you repeat your deviation explanation, please?
Yes, when the air goes through the holes, it will provide some small sound. And we have the same, do we have the same page at it? And the small sound will have some of the deviations. And since n equals to 3 has the smaller intensities, so the deviation will become more significantly. That makes your experiment have a higher deviation with your theoretical prediction.
I don't think I actually understand what you mean, but the deviations in this case could be due to a lot of reasons actually, and I explained some matters of deviation in my limits of the theory, I think. In this case, it could also be due to the fact that my theory doesn't quite account for negative pressure. So that could be a different thing in here because we increase the velocity of the holes in this case, or reduce the velocity of holes actually.
So does we have the same page that some of the deviation will cause by let's make when the amounts of the harmonics become higher, it will become a higher deviations. We have the same page as this recognition about your experiment data. Is that correct?
No, not entirely. I think those ones here are actually well, you can see a bigger deviation in the higher modes basically, and this can be it could be due to the fact that the intensity of each of these harmonics in this case was quite low, so there's probably bigger deviations because of
So for my suggestion, by reducing different sound noise, we can have reducing the deviation. So please turn on.
Sorry, I don't. Sorry, again.
You show that the air compression wave, that the air will be separated into small peaks into some certain periodically. That will cause a sound. Qualitative explanation.
Qualitative explanation. Do you mean this one?
Yeah. So, do you think that when air in contact, it will cause some small turbulence after the air is cut?
Oh yes, of course, for sure. Those turbulences, though, probably a cause of deviation to a certain extent, but turbulences in this case are very, very hard to account for.
And it will be very small and contribute into a large part about your spectrum, right?
Well, yeah, this is basically probably what background sound is, but as I mentioned before, the background sound was probably less than 5% of my fundamental frequency, which is so low that it actually.
So for my opinion, so we can excite the deviation caused by the air penetrate by adding the resonating tube, and we can also calculate the resonating tube at a certain harmonic mode that makes the sound comes from air being excited at a certain fundamental mode that we can compare it with the air comes from the air penetrate that you just here. In these cases, we can find the relationship between the two kinds of air resource. One is the compression wave, which you show here, and another is the H tone that occurs in the air goes through different holes. And here's all my
okay. Stopping there. That is the end of time. And we move straight on from a summary from the opponent. 1 minute. Start.
I think you're still muted.
can't hear you.
Okay.
Start the time again.
Thank you for.
After your permission.
Thanks for the reporter. We have discussed about some of the deviation caused by the external side with the distance of the air between the host and the microphone. It will cause some turbulence, which will relate to the airflow, and also the vortex shedding that will also occur some deviation. So by reducing the deviation, I suggest the reporter can make the microphone in front of the host. And for the external deviation, we also discussed in his graph, when the n equals to 0, the frequency will, the intensity will be higher than his theoretical prediction, and it will have a different result when the harmonic is higher, which I think it will caused by the lower intensity that is hard to analyze in his sound spectrum. And there, I also I think the reporter has lack of error bars and also the data points that there will be excited big deviations when the harmonic has a lower intensity. It does not explain, does not have the explanation about the frequency deviation. And
Thank you. Stopping there. Thank you very much. We'll go straight on to the reporter for a summary.
Yes, thank you very much for the discussion. First of all, I think it was quite well, but there was some basic misunderstanding, I believe, and some uncertainties in there. So first of all, we talked about microphone placement. In my opinion, the microphone should not be placed in front of the holes. The opponent had a different view. I actually measured this, and the turbulence are actually caused when we put the microphone in the top because of the velocity flow of the air. The velocity he stated was not constant in my measurement, which is not true. I showed that the pressure was constant, thus making the velocity profile within the tube, or the velocity over time constant. The environmental noise, because under 5% of the fundamental frequency and thus neglectable in my opinion. He also stated that no FFTs were shown, which is not true as well, and that the spectrum was not shown, which makes me believe that he didn't quite understand some of my graphs. Yes, and this wraps up my conclusion.
Yes.
Thank you very much for the.
Thank you very much. Okay, thank you, reporter and opponent. We go on to the next stage, which is where we have juror questions. So if I could ask the jurors to reappear. And perhaps the members of the teams to turn off their videos so that we can see our jurors. Okay. Going onward. Alright. So, any questions from the jury that they'd like to start with? Anything from Sunju or Carlos?
Okay,
Sunju, yep, go.
I want to ask to reporter on your slide 14 page. Can you go?
I don't think I actually have. 1 second. Yeah, I will show it. So it was page 14.
Yes. Similar periodicity, but I feel the maximum and minimum. So.
Oh yeah. Of course. Because this is not a comparable measurement in the intensities. I mean, the red graph shows the intensity of the voltage from the oscilloscope by the light barrier. So this is basically an intensity of the photodetector, while the microphone itself is the blue curve. So this is just another area of voltage. On the left side, you can actually see the spectrum of it, which is quite different for both of those measurements. So the light barrier, the photodetector gave a lot larger current than the actual, or larger voltage than the actual microphone itself. So those are not comparable in the intensities. actually see some deviation in the x-axis as well, which is due to the size of.
Okay, it's short answers here so that we can get to your questions. I think you've already answered the question. Further questions, comments?
Yeah, could I ask the reporter to go to slide 25?
Sure.
So in this one, I think you mentioned you were changing the whole number, but in this slide, it seems like the whole number is the same for both. So what causes the difference in the convolution?
Oh, I'm sorry, I actually mislabeled this. The left side is the whole number for 10 holes. Right number is for 50 holes. So this is the difference in convolution. This one here is this for 50. I'm sorry.
Okay, and a quick question to the opponent as well. So you mentioned that the reporter could have done a better job at reducing noise. How would you have reduced noise in this experiment?
I think by using the sound absorber box to reduce the noise outside, that's why for my suggestion, I mentioned about the turbulence and the spider here. I think that is quite important for the experiment, so I don't think that is kind of a deviation. The sound will also affect the analyzing and to show which is the lowest. And it can also manipulate the sound and by using the fast-forward sensor to cover the noise on the ground. That's two methods.
Okay, thank you very much.
Okay, can I just ask about the reporter? In the discussion, they talked about the error bars on slide 17 and whether there was no error bars or whether you had indicated down at the bottom they were not noticeable. You feel that plus minus a hertz is not going to take some of those points, making them doubtful?
No, I don't actually think so. I mean, vertical, this is a plot between 100 and in 100 in 100 steps, right? So it'll be 100th of the width of that one here. So I don't think it will be. Well, it's the width of the points actually. I tried to include error bars, but you couldn't really see them. So I just included the little statement on there.
Okay, fine. Further questions?
Questions of you, yeah. So your experimental part, there was no any absorber for the sound.
Any absorber in what sense? Could you clarify?
Absorbing instrument for the sound.
You mean like absorbing background noise or anything?
Yes. Not background actually. Your sound from the main instrument can reflect from some other environment from the wall or something like that. So sometimes it should be removed to get more accurate experiment. What do you think about the issue?
I think that's not big of an issue actually, because the microphone I used was a directional probe microphone. So you basically have a very long tube that is placed at a very small area. So you will reduce background noise or deflecting noise from any instruments, which is definitely there. I agree with you on that. The motor did deflect some 50 Hz tones, but this is actually not really relevant because it was isolated to the probe microphone itself. And you could see that the background noise was very minimal in my measurements as well.
Yeah, that's time. Thank you.
Okay, thank you very much. We will go away and sort out our grades and get back to you as soon as possible. So if you could minimize your videos until we come back.
什么东西？
怎么样？先把关掉，再